And a very recent paper, so this is published in the middle last year. So this one is doing in vivo studies. And these studies is use NTA and both NTA and TRPS to check the size and the concentration of the samples, CCM samples. And the customer also sends the samples to TEM. The TEM data shows that you can see this is a bar, and then it's less than 100 nanometer. But the NDA result, due to the customer sample is very complex, and the NTA overestimated the size. We see the mean size overestimated 300 nanometer. That's not true, because the TEM just average data is just around 100. While TRPS, you see here, measure the size is exactly what the TEM data image is. And in the paper, the author following experiment all follow the TRPS data, size and concentrations. Because if you imagine like this size, usually if someone like during the industrial manufacture, the last step is like the sterilized filtration. If you are this size, you cannot do sterile filtration because the 0.22 membrane will definitely blocked by this. But if you see by our data, we show that with our size, the actual sample size is less than 100 nanometer. Actually, you can use the sterilization 0.22 filter to filter your samples. This one will save money. If you use this data, you need to guarantee like all the steps must be sterile at the first time. By this, if you want to manufacture less than 100 nanometer, you only need your last step to make the sterilized filtration step. That is ready, can be qualified to sterile samples. And also, we provide like a single particle data for the zeta potential. This one is very important. As I mentioned, that the zeta potential indicates the stability of EGV in the solution. But by optical method, it just gives you average numbers. If your sample have some aggregates, optical method may not find it. For example, this sample have two groups. This sample have like around the size of 300 nanometer, but it has two different zeta potential. Optical method cannot give you, so it just mentioned give you an estimated average number. You can say average maybe around 30 millivolts, minus 30 millivolts. We can say that by this one is quite stable, but really no. By using TRPS measuring each particle, we saw that there is a group with zeta potential around minus 15. This group is not stable. It may be aggregate like in maybe a week. But if you put this into manufacture, so your things like have a part of it will aggregate in a week or because the zeta potential is minus 15, so it's very low. So it's very dangerous. So the optical cannot like serve as a QC for the zeta potential. So the TRPS you see is reported each particle's size and the zeta potential. By this, you can have detailed investigation of your samples, whether it will aggregate or not. Some people all use it for the long-term study, for the 3 months, 6 months to check the zeta potential of particles. And here is like the actual example of the calibration particles, and this is the neutral, slightly negative particles. You can see it can distinguish it. And here is an Australian customer sample of the liposome stuff they are making. We can see that it has stable part, but most of the part is unstable, which means they need to change their formulations. To guide them, they need to further modify their liposome surface to increase the zeta potential. Otherwise, the solution is not stable, even though they can prove the activities, but it's not that useful when it comes to quite low zeta potential, may not stable as an injections reagent. They need to improve that ones. That's how we help them. And this more to say that why we need to use TRPS compared with zeta sizer. Zeta sizer just give, as mentioned, give you an estimated value, and for the TRPS give you detailed information of different zeta potential groups in your samples. So compared with other technology, TRPS provides single particle resolutions. It's measuring from 40 nanometer to 20 microns. It's single particle resolution. And it can solve population in multimodal samples. This is very important. So if your samples are multimode, optical method may not distinguish that. The TRPS can do that. I can send you this slides later.
Okay.
If you need. And for the NTA, you see that the drawbacks, the large volume, and because the NTA, so optical method, for example, NTA is actually measuring the dynamics diameter. It's actually the Brownian movement. It's not the actual diameter of the particles. It's the movement, average movement diameter. That's why you see that from the previous slides, it's estimated larger than the actual diameter. For the DSL, don't use DSL. So that is a guideline set. So that is a very important guideline. So when we do publications, so we need to refer to for the guideline. This one is from the International Society of Extracellular Vesicles. They published the guideline for the researcher. So you see here, TRPS or our TRPS have what? This is not our made. This is just a code from the guideline. Have very high accuracy. So it's nearly the same result with the TEM date. And the DLS you see should not be used for the EV measurement. It's only they are like hydrodynamics in diameters. It's not actual diameters. And also you see it mentioned that techniques such as NTDLS, they measure hydrodynamics diameters. It's not actual physical diameters, resulting in an overestimation of the size. This is not our say. This is not IZON set. This all the slides is getting from the documentations. Compared with the imaging method and the current imaging date. You see here. Also, they mentioned there's no method to detect the reporting a set the LOD of the NTA because it's all based on the experienced value, just like estimates. But if you set a value, each EV particle is different, so you cannot estimate the LOD for every particle. It's not that possible. There's no method to doing that once. Also, you see that due to counting co-isolates, if the sample is not pure, if the lipoprotein and the large protein complex in it have different the parameters compared with the EV. If this sample is slightly not pure, so NTV will give you very different results. That's why, in another way, we said that we need the EV sample as pure as possible. It's also good for your downstream. Not only study, also if you downstream in vivo study, also need pure EV particles. Otherwise, if for example, if you provide from CCM with other impurities, will be do harm to the animals. And also you see that the NTA data is easily sketched. And so our recent method is that we can use a thin nanopore to measuring quite large range in the same. For example, this is one from cosmetic companies. They are using they are providing the liposome stuff. Can say TRPS can measure from 50 to around 500 nanometers by using the middle current range. This is an advanced method. If in such range, we can say that do you still remember the first picture I showed about NTA? It's more accurate in the large particle size. This one is our new device, which is different to that one. This one is made for the AAV LNP measurement. This one can down to 10 nanometers. It will be released later this year. This one is not that suitable for UV, but I just want to let you know. For UV, set of device for the other purposes like this device. So this one can say from AAV is measured down to around 20. It can do actually down to 10 nanometers. So this one is our prototype. You can see here. This is the full cell. So basically that is the TRPS instructions. So if you have any questions.
Thank you.
Basically, so I need to emphasize, TRPS need to measure the wetting the nanopore first, and then measure the calibration, and then measure your sample. Between each step, you need to clean the nanopore. Just slightly more step compared with the optical method. Optical method is just prepare your sample, preset the settings, and push it and measure. But the thing is, like, if this thing is not accurate, why, even if it is very convenient, that makes no sense.
We have some sample to measure maybe this afternoon or